Hi everyone, welcome to my new video in the Mathematics Essentials series. So in the last video I said I would discuss some properties of radicals over the next few videos. I think this will be the last one on properties of radicals because then we'll have all the properties we need to start manipulating surds. So in the last video I showed you the product property of radicals and I proved it to you. In this video I'm going to prove the quotient property of radicals. Okay, so I will show you two different proofs for this property. And the reason I'll show you two different proofs is that the first one is a bit of a mechanical brute force proof. So I just want to show you that there are often more than one way we can prove things in mathematics. And the first one, I will just kind of brute force my way through the algebra, and that's okay. But the second proof is more of a aesthetically pleasing proof because I'm actually going to use the product property of radicals, which is the property that we proved in the previous video, to prove the quotient property of radicals. And it's always nice when you prove a property or a mathematical statement and you use it to prove other statements, because that's the whole point of proving statements, either to solve problems or to prove other statements which you can use to solve more problems. So let's state the product property of radicals, the quotient property of radicals. So it says, it's going to look similar to the product property of radicals, but for any two real numbers, a and b, where a is greater than or equal to 0, so a is non-negative, but b is strictly greater than 0, so b is actually positive. Okay, so long as these conditions are met, then this is true, that the square root of the quotient of a and b is equal to the square root of a divided by the square root of b. Okay, so basically what this means is that if you had two real numbers, so long as the one in the numerator is non-negative and the one in denominator is positive, then you can divide a by b and then take the square root, or you could take the square root of a and take the square root of b and then do the division. Okay, you should always take some time to really understand what a statement is saying before you go ahead and prove it. But let's just understand why the conditions are what they are. With a being greater than or equal to 0, well, we need a real number to be greater than or equal to 0 in order to take its square root and get a real number answer. Okay, you can't take the square root of a real number that's less than 0, in other words negative, and get an answer in the real numbers. But you also can't divide by 0. So that's why b has to be strictly greater than 0, because you can see on the left-hand side of the equation in the quotient property of radicals, we are dividing by b. So if b was equal to 0, that quotient would be undefined. Now it's okay to take the square root of 0, so if b was equal to 0, it would be okay to take the square root on the right-hand side, but then the square root of 0 would equal 0, and we'd be dividing by 0 again on the right-hand side, so that's why b cannot equal 0. Okay? You can, I guess, in a way think of this as a case of the product property of radicals. I don't want to split hairs too much about this, but you can always treat division as a kind of multiplication. So you can think of this as equal to the square root of a times the square root of times 1 over the square root of b. And you might say, oh, but you still have division here, so you really haven't changed it to a, you really haven't written things purely in terms of multiplication. But the thing is, 1 over the square root of b is just some real number. So you could just call it, for instance, m, okay? And then you just have the square root of a times m. So you actually can think of it purely in terms of multiplication. And once you think of it that way, you could view it as a special case of the product property of radicals, just with some extra restrictions, because one of the real numbers can't equal 0. But I don't want to talk too much about that. Okay, let's go ahead and prove the quotient property of radicals, and this will be the more mechanical brute force algebra proof. That's perhaps not as nice. Proof. Okay, so I'm going to state my assumptions again, just like in the previous video. So to get the proof started, I need to assume all of these preconditions to hold, because the quotient property of radicals is silent. It makes no claims about when these conditions don't hold. Okay, so I'm going to assume what the blue arrow points to and show that the stuff that the purple arrow points to would follow as a logical consequence of those facts. So suppose A and B are real numbers where A is strictly greater than 0, greater than or equal to 0, and B is strictly greater than 0. So A is non-negative and B is positive. Then consider, well, I guess we could start on either side of this equation, but I'm going to start on this side. Okay? Consider the square root of A divided by the square root of B. Now, since A is greater than or equal to 0, so it makes sense to think that we would get a real number. Well, we know that we would get a real number from taking the square root of A, and square root of, well, B is positive, so we know that we can take its square root and get a real number answer, and since it's not 0, we know that we could divide by it. So what I'm getting at here is that it makes sense to expect that all of this will equal a real number. In fact, we know it will equal a real number. That's why we can introduce some notation for what it equals and call it C, even though we have no idea what C is, but we do know that it's a real number. Okay? So, let the square root of A divided by the square root of B equals C for some real number C. Now, let's see what happens when we square both sides. So we would have to put the entire left-hand side in brackets because we're squaring the entire left-hand side. And we need to square the right-hand side to keep the equation balanced. So we'll have C squared on the right-hand side. Okay? Now I'm going to make use of a property of exponents here, and I'll prove that property in some later video, but the property is this, okay, that if you have some real number x divided by some real number y, where y is non-zero because we can't divide by 0, and we're raising it to some power n, okay, well that will just equal x raised to the n divided by y raised to the n. And I will prove this in a later video about indice laws, okay? So in other words, it doesn't matter if you divided x by y, change colors, if you divided x by y and then raised it to some power, or if you raised x, raised your result by to some power n, or if you raised x to some power n and y to some power n. Should do those ones in purple so that the colors correspond. So you raised x to some power n and y to some power n, and then did your division. Okay? So I'll be using this property in the proof, and I'll refer to the property as star. So I can just write a star when I apply the property, so you can see where it's being used. So I'm going to use the property now. You can think of the x being the square root of a and the y being the square root of b. So square root of a squared divided by the square root of b squared. Okay, so we had this kind of setup on the left-hand side, and we've rewritten it like this. All right, but on the right-hand side, we're still just left with c squared. Now those squares are going to undo the square root, So in the numerator, we'll just be left with a, and we can drop the brackets as well, divided by b, okay? And that's still just going to be equal to c squared. But now we can take the square root on both sides. So on the right-hand side, we'll have the square root of c squared, and on the left-hand side, we'll have the square root of a divided by b, square root of the quotient of a and b. And on the right-hand side, the square root will undo the square, and we'll just be left with c, and we'll just still have this quotient a over b on the left-hand side. But now you can see that we started off by letting the square root of a over the square root of b equal c, and we ended up reasoning to this down here, where c was also equal to the square root of the quotient of a over b. So that means what the red arrow points to must equal what the green arrow points to, because both of them equal c. So we can conclude, therefore, the square root of a divided by the square root of b equals the square root of the quotient a over b. And we can relish in writing the square to say that our proof is complete, because we've shown what we set out to prove. Now, I'm just going to section this off. And remember, that's what the quotient property of radicals claimed. Okay? As long as a is greater than or equal to 0 and b is strictly greater than 0, which is what we assumed, we're able to show that this holds. Okay? Now I'm going to prove this property again, but this time I'm going to use the product property of radicals to prove the quotient property of radicals. So I'll write the product property here in blue, product property of radicals. I'll just call it the product property to save writing. Okay, remember, for a and b in the reals, where a and b are non-negative, we know that this is true, that the square root of the product of a and b equals the square root of a times the square root of b. I think in the previous video I wrote it the other way around, as in like this was the left-hand side and this was the right-hand side, but that doesn't matter. Okay, so we will use this property here to show or to prove the quotient property. And I realized I didn't write the green star where I said I would. So we applied this property, the green star, we applied that here. Okay, but I'm sure you knew that. Anyways, let's prove the quotient property of radicals by using the product property of radicals. Okay, proof of quotient property of radicals. Don't know why I used a capital Q for quotient, but what's done is done. Okay, so I'm proving the same thing as what I've just proven, but I'm going to use the product property of radicals in the process. All right, so again, let's consider the square root of a over the square root of b. Okay, and we can write this as the square root of a times the square times 1 over the square root of b. Okay, so that's just like if we had let's say 2/3, we could write 2/3 like this. We could say 2 times 1/3. Okay, that's what we've done. Now let's just do some reasoning over here. Okay, we know, I'll write this in blue, we know that the square root of b is greater than 0, So we know that we can take the square root of b and get a real number answer, and then divide 1 by that answer and get a real number. Okay, we know that the 1 over the square root of b is well defined. So that means we can just give whatever it all equals a name. So let's just call it m. Okay, and let's square both sides. So when we square both sides, this is what we'll get. And distributing the square on the left-hand side, we'll just get 1 squared in the numerator, no need to write that, over the square root of b squared, but the square will cancel the square root, so we'll just be left with 1 over b. And that's still just going to be equal to m squared. Okay. And then we can take the square root of both sides, and we would be left with the square root of 1 over b equals m, because when we take the square root on the right hand side of m squared, it will undo the square. Okay, but notice we started off, before I took the square on both sides, this is the first line of our reasoning. We said 1 over the square root of b was equal to m, and then we squared both sides and we got this line. So I just wrote it again to make things clear. Okay, here's 1 over the square root of b. Okay, and that's equal to m. All right, but m is also equal to this, the square root of 1 over b. So that means we can take this whole thing and replace it with this thing. Okay, so let's do that. I'm going to leave those blue arrows there so it's easy to follow. Maybe it gets in the way, I'm not sure, but I'll just leave them there. Okay, so we have the square root of a times the square root of b. What we're going to do is make this substitution. We're going to substitute that for that. Okay, so we're replacing 1 over the square root of b with the square root of 1 over b. Oops, I left out the square root of a. Okay, the square root of a times the square root of 1 over b. Okay, maybe I will get rid of all of this blue. Okay, maybe that's nicer to look at. Okay, now I don't really need to make this substitution, but perhaps I will. Okay, we know that 1 over the square root of b is just equal to m. Okay, so I don't actually need to make the substitution for the proof to work, but I will just so it's more clear how I'm applying the product property of radicals. I'm just going to replace this 1 over b underneath the radical with this m squared here, okay, because it is equal to 1 over b, okay? All right, so this is unnecessary, but it will just make it easier to see how the product property of radicals is being applied to prove the quotient property of radicals. So square root of a, we have the square root of 1 over b, but we are replacing that with m squared. Okay, now you can see that the square root of m squared, well, that square root will just cancel the square, but I don't want to do that because then I'll just be left with m, and there'll be no way for me to apply the product property of radicals. So I actually want to leave it the way that it is, and then just say, I actually don't need to keep writing the left-hand side, and just go ahead and apply it now, because what do we have? We just have some real number a, right? And we're taking its square root, and we have some real number m squared, and we are taking its square root. Now, we know that m squared is a real number, and that it makes sense to take its square root. So, and we know that it's strictly greater than 0. We know a is greater than or equal to 0, and we know that m squared is strictly greater than 0. Okay? So we can apply the product property, because the product property says that so long as you've got two real numbers that are greater than or equal to 0, then the square root of one times the square root of the other will just equal the square root of their product. So let's write it as the square root of their product. The product of a with m squared. Okay? But remember, m squared was just 1 over b. Here, m squared was just 1 over b. Okay, so we're just going to substitute it back in. I just made the swap for m squared so you could see the application of the product property. Okay, so that's where we applied the product property. We could have left it as 1 over b. Okay, so square root of a, all right, m squared is 1 over b, so this would be times 1 over b. We still need our square root. But a times 1 over b is just going to be a over b. All right, and we're still left with our square root. Okay, but if we go back up to the top line, we started off with this, the square root of a over the square root of b, and we did a bunch of reasoning, and we found out that that ended up being equal to the square root of the quotient a over b. And that's precisely what the quotient product of radicals says. So we can write another square to say that we're done with the proof. So that is the quotient property of radicals proven by using the product property of radicals. Okay, and some of this stuff that we did over here in blue was not necessary. Okay, just may not have been clear how the product property was being applied. Okay, we would have had to do a little substitution, but we didn't have to do all of that. So for instance, I didn't need to use m squared. Okay, but maybe that made things a little easier to follow. Okay, so just to recap what we did. All right, so we stated the quotient property of radicals. Okay, and we observed that it bears a striking similarity to the product property of radicals. Okay, then we proved it. We did 2 proofs. The first proof was quite a mechanical brute force algebraic proof of really just crunching the algebra, and it was quite structurally similar to the proof for the product property of radicals, which I did in the previous video. Okay. Then I just restated the product property of radicals from the previous video so that you could recall it for our proof in the quotient property, because we used the product property of radicals to prove the quotient property of radicals. Okay, we started off on one side of the equation in the quotient property of radicals. We did a bunch of reasoning and found out that we could produce the other side of the equation. And that concluded our proof. So if you found this video helpful, feel free to like and share it with your friends. And if you would like a notification when I upload another video, subscribe. Until next time, bye for now.